So as we continue on with Module 6, looking at the topic of static body stresses, we're going to take a look at within this module, looking at body stresses within a member as a whole, as distinguished from the surface or contact stresses located in regions where the external loads are applied. So within this module, what we're going to look at here is primarily we're going to take a look at direct shear loading, continuing on where we left off in the previous module, and then also bring in some information with torsional loading as well. We'll also be looking in the next couple lectures at some pure bending, stresses, and Moore's circles. Now, if you're relating back to your textbook right here, this is chapter 4, and this is sections 1 through 14 for your reading assignments. So again, this relates back to chapter 4 in your textbook, discussing the topic of static body stresses. So as we continue on with the topic here of direct shear, I want to take a look at a couple different practical examples and then go through a couple problems together. So one example right here we have these two pieces of material. They may be the same material, they may be different types of material, but we can see right here we have a bottom material right here and a top material right here sandwiched together, similar to some of the problems we've seen in the previous module there. And now we can see we have this load P and this equal and opposite load P up here on the top and bottom materials respectively like that. And we can see we have holding these together, we have this nut and bolt combination here. So we can see as we tighten this bolt down here, it increases the force on this. So that's a whole nother problem that we could look at right there when we discuss how tight we can go with this nut right here and what the compressive force should be based upon those materials, not to damage the material, things of that nature. But that's a separate problem there. But in this design class, are things that we want to start thinking about, not just the one isolated issue, but all the combination of issues that we may have and different ways to design things. So let's just take a look. This is a direct shear problem though. We can see, okay, we've tightened that down to the correct torque specs right there. We have this material right there. Now the question may be a couple things. We could ask ourselves the question of, okay, what is the shear we're going to see here on this bolt right here, if we already know the material, or we say, okay, we know that these loads are going to be, we can back out the shear right there that we're going to experience on this bolt, what material should be, what diameter should be. So whether we're given the bolt material, the bolt diameter, or this external load, those are all things that we could solve for. It might be a problem where they tell us all the material types, all the diameters, all the dimensions, and they say, what is the max load that we can see here before we damage or before whatever may happen right there on the bolt. So those are all different types of things that we could do within a problem like this. But this is just one application where we have direct shear occurring here. So let's talk about another example of direct shear that's very popular within design. So this may be something you actually might see within your design project for the semester within this course here. Maybe something you'll see as you're working for a company in the future or some type of design research project as well. A very common bolted joint right here. This is a case right here where you may need to have a pivot along this axis right there before the shearing occurs right there. And you want to ask yourself, okay, what do I need to do to design something like this? I may know all the rest of my project, and it comes down to this. We got to think about, okay, what type of bolt do I need to use? What are the dimensions of that bolt? What material am I going to use for that bolt? All that type of information right there. So it's a question of which type of problem are you looking at within this here? Are you looking to solve for what is the max load that this can take because this already exists? Or are you saying, okay, I know what the max load is going to be because I've already designed the rest of my part or assembly or product, whatever it is, and I need to figure out my last thing here of what type of material, what diameter of bolt can I use, can I put in this here? So those are those types of problems there. But what we can see now here is you have these two top ones up here. As the load goes this way, it's pulling there and there on the bolt there, and this one here is pulling right here on the bolt right there. We have these two areas right here, we have our shear. So this is something that we may want to consider within our design of a larger product, a larger part, an assembly, something of that nature. So now let's take a look here at an example for direct shear. So this is a great practical example right here. And right in this problem here, what we can say is, okay, we already know for this bolted joint right here, we already know the external load right here, 50 kilonewtons. Now this may be something that we've calculated previously for the rest of the part or the product that we're designing. It may be something where we as a design engineer, as a part of a team, our particular part of the design project is just to spec out this bolt right here. And we got to figure out the material, the average stress, things like that right there. So that's just our part, and somebody else has already calculated the rest and is given to us. So those are two different scenarios where we may end up in a situation where we're just looking at this bolt right here. Maybe that we've already done the rest of the calculations for the rest of the product, or maybe that other team of engineers has already done that, and this is our part right here is to work on this design aspect. So with that there, they've also already calculated out for some reason, whether it's a spec or where they've already done the calculations here, that we need this diameter of the bolt to be 13 millimeters. Now, typically in the design process, I would say that's something that's going to change back and forth. And this may be as we talked about the design process and the iterative design process that we go through with those different cycles, where we might say, okay, we've gone down through, we calculate out our average shear stress right here, and then we find out, well, that's not going to work for us. We're going to need to go with a larger diameter bolt. And we go back through the process again, because the design process is iterative, as we've seen before in the previous modules and lectures. So with this one here, we have our load. We have the diameter set and give it to us, and we want to find our average shear right there. Well, in order to find that average shear, if we've already got that diameter, we can calculate the area right here. So the area of the bolt are A sub B for area, and B, the subscript for bolt. So again, that's something else I do want to stress. Again, pay attention to your indices, and if you're making them up yourself, make sure something that's intuitive and you write down what that means. So this is area of the bolt, A sub B. So we've clearly labeled that right there. Now this is equal to, if we're dealing with our diameter here for area of a circle, it's pi d squared over 4, where we now have our diameter. If we wanted to use our radius right there, just make sure we divide our diameter by 2. For this one here, we're just going to use our formula with diameter, so pi d squared over 4. We do that out, and we can find now we have a numerical value for the area of the bolt. So our cross-sectional area of the bolt is 132.7 millimeters. Now pay attention here. We're dealing with millimeters here and kilonewtons up here, which is in terms of meters. So make sure we do our conversion before we do our final calculation right now. So we look at this here and we say, okay, well, what is our formula if we're trying to look for our average stress? Even though this is a simple problem right here, we can go back to that setup page. What am I given? What am I looking for? Based upon that information, what is my general governing equation that I can use for that there? So we take a look at this here and we say, okay, well, our average shear is going to be equal to P over A, but this is 2A. Now, why is this 2A? Well, it's because we got these two shear planes right there. So you got the top and the bottom plane right there. So now our tau average stress is equal to P over 2A sub B right there. And we can plug that in. Now, this is in 50,000 kilonewtons. We convert that to newtons. It's 50 kilonewtons. We convert that to newtons. It's 50,000 newtons right there. All over 2 times our area that we've just calculated up above here of 132.7 millimeters. We can plug that in. We do our unit conversion correctly, we end up with a value for our average shear stress right there of 188.4 megapascals. Now there's a lot we can do with that information there. We can go back to some of our charts and then decide, okay, if I know that this is going to be my average shear stress here, ask yourself 2 questions. Is the material that they've told us correct? Do I need to specify a material? And if the material that they chose us is set in stone, maybe we need to go back up again to that iterative process and change right here our diameter and make it bigger. Or maybe it weighs too much based upon that, and we need to go back and see if we can get smaller but still stay in the right range for all of our values. So this is how we use this general simple equation right here for average shear stress for an example of direct shear on a bolted joint right here with 2 shear planes for the design process. So let's take a look at another example problem here for a different type of direct shear. So in this problem here, they tell us that we know that we have a force P and it's in a bolted or pinned joint that produces a shear failure in the bolt or pin. So again, we're looking at the bolt or pin, and that's what we're focusing on right there as far as our design process goes for this. And again, these are questions of, do we have the right material? Do we have the right diameter? All those type of things. Can we change the max load requirements? Things like that that are questions we need to ask ourselves within the design process. What's set in stone? What are the specifications that we have to maintain? And what are things that we can vary in order to meet those specifications within this here? And again, we go back to that iterative design process that we talked about before. So in this case here, the bolt or the pin right here are made of a steel of known diameter. So now we know that it's steel and we know the known diameter. So now what we can do with this steel right here, we can select the type of steel, and we can do this by going to Appendix 4A. So C4A in the back of our textbook there. Or there's other reference diagrams as well. If you don't have this textbook here, there's a lot of other tables and charts that we could go to. But for this here, let's use our textbook chart, Appendix C4A. And what we need to do is determine the force P required to produce a shear failure in a 0.75 inch diameter. So if that's the diameter of our pin or bolt, with the configuration shown here. So we need to specify a type of steel and determine the force P required to produce that shear failure in that there. And this is a more realistic process where we're going to be back and forth and comparing those two together. Well, if I go with this steel here, it's going to cost this much, it's going to weigh this much, it's this easy to obtain, things like that right there. And this is the max force that we can determine our force P based upon everything else in this diameter of 0.75. So we need to go back and forth and figure out the best combination that fits everything within our design criteria and specifications. So this is a more realistic type of problem where you have that back and forth. You have that freedom between which type of steel. We know it has to be a steel, but which type of steel from that right there. And then from from that right there, we also want to determine what the force is. Once we have that type of steel specified, what is that force that's required to produce the shear failure in a known diameter bolt? So we come down here, here's our given schematic and data down here. Okay, so we have this load right here, P, equal and opposite on both sides of this right here, that material there. There's our steel bolt right there, and this is our diameter of 0.75 inches. So the first step in this process right now is to go through and create our setup page. I know there's not a lot of information, but this is going to be very helpful because not only are we putting in all the given information what we're solving for, we have a simplified version of our diagram we can reference back to, and we have a lot of assumptions. So the problem like this, because it is so simplified, there's a lot of assumptions we need to make. We need to understand what those are and how they relate to our problem when we're going through our solution. So we have here, okay, what are our known information? So I write out here, there's my given, and again, if this were a homework problem, you'd have your name up here, what the problem number was, when the due date was. So you have right here, okay, my diameter is known, and that's 0.75 inches. My P is my force right there, and we know we're dealing with a material, a steel material right here, which we need to select from appendix C4A in the back of our textbook. There, we redraw out our diagram right here. So here's our diagram right there. There's our bolt and our nut right there. There's our load P right there. And we can see, okay, there's our diameter right there. So what assumptions are we going to make within this right here? So we can assume that bending is negligible. We're going to be purely in shear right here. We can go ahead and assume that the plate interface friction is going to be negligible. So that friction between these two plates is negligible. So as you can already see, that's not realistic. This is a very simplified case, but just for the sake of this problem here, we're doing that there. We're also going to assume here that the bolt and pin materials are homogeneous. That can maybe be the case, maybe not, but that's a realistic assumption that we can make right there. And we're assuming that the loading is static. So that's something that's also a big assumption right there. That's a static load. There's no dynamic load. There's no impacting. And then we're also going to assume in number 5 right here that there are no residual stresses. And in 6 right here, the shear strength of the steel bolts right here, we're going to assume we can use this relationship here. We have our S sub US, which is our ultimate shear strength. And this comes from equation 10.16. on page 314 of our textbook right there. This is approximately equal to 0.62, because we're dealing with a steel right here, times our ultimate strength right here, and they're assuming that this is going to be accurate for this analysis right here. So this approximation of the shear strength of steel bolts, this equation from equation 10.16 in our textbook, is going to be assumed to be accurate for our analysis right here because we're dealing with a steel bolt. So again, depending on what you're dealing with, there may be a different assumption, a different relationship you're going to use here, and that relationship between our ultimate shear strength and our ultimate strength over here. So now that we've had the opportunity to read through the problem, kind of get an idea of what's going on, create our setup page with everything that we know, everything that we're looking to solve for, and all the assumptions we're making, along with kind of our governing equation within one of those assumptions right there, we can now begin our solution. So looking at that information, we say, okay, we know this, we're trying to solve for this, so what equation can we utilize in order to do that? So what I'm going to go back to is I'm going to use equation 4.2 on page 79 to 80 of our textbook right there. So what we can see within this here, we can set our tau equal to our ultimate shear strength right here, our SUS, and again, we're doing the SUS from that equation that we saw before, where we're looking at this relationship right here on the previous slide from that assumption. So equation 4.2, what is that? So equation 4.2 in our textbook simply says that tau is equal to load over area right there. P is our load, A is our cross-sectional area right there. So we can plug in again our shear strength right there. We can now set this equal to tau right there. So we can plug this right in from our previous relationship right there, plug that in for SUS for our tau right there. We have our area that we can plug in right here. So we can talk about this for a bolt right here. Let's go with a little side section right here. So if we have this over here, we have our bolt right here. Area is equal to pi r squared. R is equal to d over 2. So r is equal to 0.75 over 2. So our r right here is 0.375 inches. So that's what we're going to use when we plug this in, is 0.375 inches, because we're dealing with radius and not diameter. So we can plug that in there, and we can say, okay, this is equal to pi times right here 0.375 squared for our radius squared. So area right here goes in like this here to this, so we can plug in that relationship. So now this equation right here, which was originally our equation 4.2 right there, P is equal to our pi times our 0.375 squared times, this is our area right there, times our 0.62 SU, which comes from that relationship on our assumptions on our setup page right there, which we can now say is equal to our tau right there. So that goes in right there for now our load value right there. So this is where we can go now to our chart, C4A in our textbook, select the correct steel that we want to use, look up our SU value right there, and we do that, our SU is going to be 90 KSI. So we can plug in 90 KSI right there, multiply it by 0.62, multiply it by that cross-sectional area in order to get our load right there. But again, this is our design process right here where we may want to take a look at that chart and really think about, okay, what steel are we going to use? So what SU? So that makes this a great problem right here that we can go back and forth with that problem right there. And this is something we could use MATLAB, we could use Excel, and we can have a list of these different SUs for different types of materials, and look how it plays out with our tau, or with our p-value right here, with our load right there, and say, okay, yeah, if we know we want a higher load, maybe we need to go up with our value for SU for different types of steel we want to do. So now let's go take a look at that chart, C4A. So we go to the back of our book. This is chart C4A. So we have a bunch of different ones. I've got a small section of this right here. I've rewrote out my equation right there, and we can see that, well, if we went with a 1040 as rolled steel right there, we can get that strength right here in KSI is 90 KSI right there, and we could plug it right in. That's great. And we can go through that whole process right there when we plug it back into this general equation for 90 KSI for if we chose a 1040 steel right there. Say P is equal to pi times our R squared right there, which is our cross-sectional area, times now, this is our 0.62 times our SUS right there, so we can plug, times our SU right there to get our SUS, which is equal to our tau value for this case right here. Well, we can get that 90, plug it in right there, and we find our load is equal to 24,651 pounds. Now, maybe that was too high, maybe that was too low, so we could go back through and say, well, maybe there's a better type of steel. Or maybe this type of steel right here that meets the specifications, but it was too hard to find. It was too expensive. It weighed too much. So what's another option? Maybe we don't want to use a steel. Maybe we want to go to a different type of composite. Maybe we want to go to a aluminum, something like that there. So depending on your design criteria and your specifications, you can play around with this now, and you can play with that, look at that load with your values here for each different type of material. So that's part of that iterative design process that we discussed right before in previous lectures and previous modules. We're looking at this here. So this is a great relationship from a very simple equation right now where we can look at both of those right there and say, oh, that's not quite the load I wanted, or actually that's way above what we're going to experience. I could get away with something cheaper and lighter. Something like that, where you can play around with that there until you get it right. Again, thing to think about with this here, because we're talking about the design process as a whole, is your safety factors. So even if you're like, wow, this is like 3 times as much as I'm ever going to experience, well, maybe you want that in there because you're doing this event. Look at your assumptions. A static loading. What if it was a dynamic impact loading? Is your product, is your part going to hold up to that? So pay attention to all that. And that's why I always talk about your safety factors as a consideration from the beginning of the design process and not an afterthought at the end. You can always assume, like we talked about before, that somebody is going to use your product outside of its intended purpose. So now let's take a look at an example here for a pin joint. So we went through a basic version of one of these earlier. Let's expand upon that there with some actual numerical values and a more realistic application right here. So in this problem here, it's a little bit reverse of the previous problem we just went through in the fact that now they're telling us the load. So now it's information that we have the load right there, and we need to back out what the pin should be within this right here in order to find the minimum pin diameter required to avoid that shear failure. So this is a realistic application. We've probably already designed this part as a whole, and we're looking at this last little aspect over here of what should we use for a pin within this here. Now within this one here, they have specified to us what type of steel. So that makes it a little bit less realistic here. Normally we would have control over the diameter and the type of material that we're going to be using for the pin right here, and we could play back and forth like we saw in the last problem right there between those two until we optimize that along with our criteria for our cost, weight, things of that nature. If there's a corrosive environment, where we have to use a stainless steel. So all those environmental factors, cost factors, weight factors would all come into play. For this one here, let's just say that's already been done for us, and they told us for whatever reason we need to use a 1040 steel right here. So we can go to that same chart, we looked it up, or we can go to the manufacturer of that bolt right there, that product, and we can say, okay, our SU right here is 90 KSI. So we've already done that. We've looked at that table C4A right there. We've looked that up for a 1040 steel right there. We know it's 90 KSI. Based upon that formula, we can say that now SUS, based upon our assumption right here, is equal to 0.62 times the SU right there. So that is equal to our tau right there. So with that right there, now we can go through and determine our diameter, our minimum diameter of that pin required in order to avoid that shear failure right there. So we look at this right here for our given diagram right here, and we can say, okay, well, I have this external load. Now I know the value. That's the main difference in this problem, kind of working in reverse right here. And this is 12,325 pounds. And I'm trying to find now the diameter of the pin based upon the fact that I know the material as well. So what are the assumptions we can make within this one here? Well, we can assume that bending is negligible again. We can assume that the plate interface friction is negligible. We can assume that the pin material is going to be homogeneous. We can assume that we're dealing with static loading right here, and that there's no residual stresses. And again, we can assume that this relationship is going to be accurate for our analysis. Again, a lot of assumptions. In reality, it might not always be static. It might not be homogeneous. There's definitely going to be friction. There may be some bending because we're not quite pulling in pure tension right there. And, you know, maybe this is not quite accurate for our analysis based upon all those. But for this problem here, in simplicity's sake, that's what we're going to do here. This is something to take a look at. If you were doing this as a comparison to an actual test, a pull test on this part right here, maybe you put this in a tensile testing machine and you took a look at it, and all of a sudden your values are not right. You're looking and said, wait a minute, you know, this is not what I should expect to see. This is at this load, I should expect to see this shear, and this is what I'm experiencing. Instead, when I look at my stress strain graph, you know, those things don't look quite right. Well, that's because there are these external factors that we have not accounted for within these assumptions right there. We're assuming that the material is homogeneous, and maybe it wasn't quite homogeneous. We're assuming that that diameter is constant the whole way up, and maybe it didn't quite. We didn't take the calipers to it, and it wasn't quite there. We didn't take the friction into effect at all, and that's definitely going to come into play as we look at this here, especially because we're going to actually have to do a whole separate problem when we calculate that friction based upon the force we're getting pushed in on the parts right here like this from how tight we have that nut and bolt combination right there. So that in itself is another whole problem that we should be solving for. Is, okay, we have this torque spec here, and we come down here, what does our load applied to this, and how does that load apply here affect our coefficient of friction within this here? And then we can pull sideways like this and say, okay, we have our coefficient of friction times our normal force pushing up on that. How does that affect everything else? So those are all things that we need to consider right now, and we'd have to do a whole free body diagram for that. We're not going to do that, but I want to address it when I talk about this problem here to see, as you apply this to your actual group projects for the end of this semester, this is something that you do need to consider with that there. And if you make this assumption here, there's got to be a good reason why you're making that assumption. You've got a really good lubricant. You have, you know, you've loosened this up to the point where it moves freely within it, all those types of things, you know, and if you do that there, is then there a gap? If you've loosened enough, is there a gap in there? Or is that gap distance negligible? So all those things are realistic applications that we're kind of ignoring with these large assumptions. So from this here, based upon all those assumptions that we're going to make, we write out our setup page. Even though that problem statement there was pretty close to a setup page, I'm still going to go ahead. This is our problem number. This is problem 411 right here. This is our given information. We know we have this external load P of 12,325 units of pounds. We know we're dealing with a 1040 steel. We have our SU value here of 90 KSI. Based upon our assumption right here, we have this relationship to get our SUS right there, which is going to be 55,000 PSI when we multiply our SU by 0.62. So now we can find, we have a minimum diameter pin here that we need to find. So this is what we're looking for, is we need to find the minimum diameter of our pin to avoid our shear failure right here. So I redraw out my given diagram right here. So I have my load going off in this direction here, and I have a load going off in this direction here, equal and opposite right there, which I can correspond right up here. I don't write my numeric values, but I can look back up to my givens. That's 12,325 pounds, and this is the diameter that I'm looking for right here of the bolt. Then I write out all my assumptions again. Bending is negligible, no friction, homogeneous, static loading, no residual stresses, and we're using this relationship right here. So now that I've had that opportunity to go through, read through the problem statement, look at our initial given diagram, understand everything that they're asking me to solve for, have it all organized right there along with my assumptions, I can now take a look at that information and say, okay, where do I go from here to get my governing equation and start solving this problem? Well, we can use our same governing equation we did before, equation 4.2, where we have our general equation here as tau is equal to P over A. So our shear stress is equal to our load over area, where, again, for our case here, our shear stress is going to be equal to our SUS right there. So tau is equal to SUS. We've already solved for that SUS from the previous statement right there, we see that this is equal to 0.62 times our SU. We got our SU by going to that chart, C4A in the back of our textbook for 1040 steel right there. We looked that up for 1040 steel. We found that was 90 KSI. So we take and multiply 90 KSI by 0.62, and we end up with an SUS right here of 55.8 KSI, or 55,800 PSI, which again corresponds now to our tau value over here. So we have our load that's we known over here that we just brought back from our first setup page right there of 12,325. We have our SUS, or our tau value there. So we can replace our tau with our SUS in our governing equation from equation 4.22 in our textbook right there. So now we can say that, okay, this is equal to 0.062 SU, or over here when we do that math out, 55,800 PSI. Pay attention to our units, and this is equal to our P over A. Well, we can rearrange that. So we can rearrange that and solve for our area, because we want to back out the diameter of the pin. So we want our area on its own, and then back out diameter from that. And this is equal to P over that 0.62 SU, which we've already solved for up here. And we can say, okay, well, that's equal to, now plug that in right here, 55.8 KSI. So area is equal to load over that 55.8 KSI right there. So we can say now, if we want to convert that, because this is in pounds right here, convert that to PSI right there when we do our calculation out. Area is equal to 12,325 pounds, which is our given load right there, divided by now our tau value, or our SUS, or 0.62 times our SU. Again, I keep bringing this up just because I want to reiterate all of that for you guys right there, where that came from right there. Plug that in now, and we can now solve for our area. So we continue on with that there, and we say, well, area for this right here is equal to 2 pi r squared. We want to back out that radius right there. So we can say, okay, now I've converted this to PSI, so we have pounds and PSI, because we do out our unit analysis. We want to make sure we come up with this correctly. 12,325 pounds divided by 55,800 PSI. So now we can say, okay, well, let's plug that in right here. Let's rearrange this slightly over here, get r on its own, and move our 2 pi over the other side. So r squared is equal to 1 over 2 pi times 12,325 pounds divided by 55,800 PSI. Take the square root of both sides, so r is equal to the square root of 1 over 2 pi times our 12,325 pounds divided by 55,800 PSI. So we solve that out. Do that by hand, plug in your calculator, Excel, MATLAB, your choice. R is equal to 0.1875 in inches. Double check your units. Pounds, PSI, yes, we're in inches. Yes, that's what we expect right there. Well, they didn't ask us for radius. We go back to the setup page, they asked us for diameter. Recall the relationship. The diameter is equal to 2 times our radius. So diameter is equal to 2 times that. Now we solve for that radius right there, 0.1875. So our diameter right here is 0.375 inches. So now we've solved for what they'd asked us to solve for in this problem statement here. But this is something right now where we may have to go back and say, wow, that's kind of crazy. If we know we're at a 1040 steel and it's this diameter right there, maybe that weighs too much, maybe that costs too much, maybe that's a hard bolt to find, whatever it is. So let's go back, and maybe they didn't give us the material type in this problem. We need to go back and forth between that diameter and our material properties right there, and keep going through this equation until we find that right combination that meets our weight, meets our specs. It's non-corrosive, corrosive because we're in a saltwater environment, whatever it may be. And that's how we really work this in the design process. Keep going back through that until we have the right combination of material and diameter that meets the criteria for that load or that stress right there that we're dealing with. So now the next topic I want to get in here is torsional deformation. So now let's take a look at it right here. We have a member right here, a simple cylinder right here, a rod right there, and we can see we have our equal and opposite torques applied to either end of it. And we have this, and we can see right here we have our grid pattern on there. We have our mesh in there. And we want to take a look at this right here and say, okay, after deformation, after we applied these two torques right here, what does this look like? And if we didn't have these grid lines on there, it'd be kind of difficult to see how it deforms. That's why I like that we have these grid lines on here, and we can go back to everything we talked about when we were talking about axial deformation right there, and we can look at these grid lines, and you can use that information to take a look at how it deforms, where it deforms along the length of it. Things like that are going to become very important, the same as when we looked at axial deformation right there. And then we can go back to that grid sensitivity issue right there, which we've related back in course ME83 as well with SolidWorks right there, and talk about, as we do this mesh refinement right there, how does that affect our accuracy if we're looking at FEA of something like this here, based upon the information of how we find how that deformation propagates through this with the length. So as we continue on with torsional deformation right here, what we want to talk about is our angle of twist. Now we discussed this previously in our early modules. This comes back to us here. And as we talk about this related to the torsional deformation of this member right here, so let's take a look at this rod that we're dealing with as our example right here. We'll talk about the distance. We want to see what is our torsional deformation as a function of our distance from our end over here. So that's why we can see this is phi of x, our angle of twist relative to our distance x. So how does that deformation change as we move further away from the end of our rod right here in this particular case here? Now this is the angle a radial line is going to move through right here, and we're discussing our angle of twist. And this is at a cross section A, some distance x from our end right here. So we can see right here, if we're looking at this right here, this is our cross section right here. Right there, some distance x from the end over right here. So again, this is again where we talk about the importance of grid and sensitivity and our mesh refinement right here as we're looking at this right here. If we only look at this, in 5 different sections along here, we may not get all the different information right here. So then we go to 10, then we go to 20. So we want to eventually get to an infinite number of sections along right there, or get to a point where we don't see any changes in our stress or changes in individual sections right here in between these different layers, or minimal changes within those as we refine our grid right there. So as we change that grid sensitivity right there, as we're talking about our mesh, as we're going into finite element analysis in a different program like MATLAB or something like that. If we're doing it by hand, we might just say, hey, okay, we looked at it at a centimeter away, we looked at it at 2 centimeters, 3 centimeters, whatever it is from our end distance over here, and we get down here and we see, okay, for that applied torque right there, once we get past 2 centimeters right here, we don't see much. But maybe between 1.9 and 2.1, we see, okay, there's not much change right there. Maybe we need to go 1.81, 1.82, 1.83, and really find where we don't stop seeing that angle of twist right there, change right there based off that x distance. So that's something we do want to consider, is what is that distance x? If that's a question that we're asked, like how far away can you get with this applied torque before you start seeing a deformation over a certain amount, then that's something that's important right there, is how far out, what increments we're using. And we consider, like, can we do that? Or maybe we find roughly what it is by hand and then go in there and look at it a little bit more finely with FEA analysis using a program like SolidWorks. So there are some assumptions that we need to make when we're talking about our torsional deformation. Some of these assumptions include the fact that our cross sections remain perpendicular to the longitudinal axis. So we saw that in the previous slide right there where we were dealing with that rod right there. We saw our longitudinal axis going right up the center of that rod right there, and we saw that all of these cross sections that we were looking at right there at that distance x, particularly in that example problem, was perpendicular. So that's an assumption that we make, that all of these cross sections need to remain perpendicular to the longitudinal axis. We're also going to make the assumption that radial lines within the cross section remain straight. So all those radial lines as we're going out around that cross sectional area right there are going to remain straight. And we're also going to assume that the length of the cylinder and its radius do not change. There's going to be very, very small strain. So as we're applying those torsions, we're assuming that that length of that overall length of the cylinder is not going to change. So that's a larger assumption that we're going to need to make there, not always true. And that's based off the assumption that these strains are going to be very small. So the next thing we want to do with our torsional deformation is similar to what we did with our axial deformation, and take a look at an isolated element at some distance, at some area of interest on our rod or our sample right here. So we can take a look right here and we can see we can isolate this element right here. So we have our element right here. It's some distance right here, our rho right there, away from a center axis right there. So rho is the distance from the axis of the shaft right there, and with some distance right here, right there away from the fixed end down here where our reference point is. And again, we have down here our axes right there, and we can't forget our right hand rule as we're going through that, and we'll go over that again in a little bit. We want to discuss right here that we really want to have this reference point, understand that everything is going to be referenced from one area, one axis, one length right there, one fixed end right there, so that we know what all of this information is as far as our variables go. So if we're trying to locate this isolated element right here, we can see, okay, it's this distance rho away from our center axis, it's this distance x away from the fixed end right there, and it in itself has this distance of a delta x, so that where the end of this element is, one end is at x and one end is at x plus delta x, if we're referencing back again off of that location at the beginning there, our fixed end right there where everything is measured from. So that's something that's going to be important to do. Then we apply the torque right here, and we can see, okay, how does that element change? What changes with that element there? And we talked about the strain being minimal, so we're assuming that these distances aren't going to change. It's going to be fixed from the assumption we made before right there. So then we can take a look. Once we've isolated this element, we know where it is relative to our entire member right here. We can then go and proceed through with our analysis. So now let's take a look at an individual element right here within our member right there. So we want to take a look down here. What we want to look at here, we can see highlighted in red and green. Before deformation, we have this angle phi of x, and this angle phi is going to be dependent upon how far we are from the fixed end of the member, based upon that distance x right there. And after deformation, we have this change in our phi right there, our delta phi right there. We can see our whole member has this length delta x that we discussed in a previous slide right there. And we can see now we originally were at this A, B, C right there shape of this, and then after deformation, we go now to this A, D, C right there, and we'll discuss those angles and stuff in a minute right here. Right now what I want to look at for this element right here is the back face. This back face is going to rotate by this relationship here, phi of x right there, and the front is going to rotate by phi of x plus our delta phi right there. So it's going to be based upon that right there, and again we can see that the delta phi right there is based upon after deformation, our green lines that we see off in our diagram. So from that, what we want to do is then talk about our shear strain, our gamma. So our gamma right here, we can see this up top here, and we can see that this changes, and again, this is going to relate to our phi and our phi sub x right there. So we can see as that angle changes right there, our gamma is going to change. Our gamma is our shear strain. So our shear strain across the element due to the difference in our deformation or our delta phi right there. So we can see that delta phi right there as we go, we can change that angle right there. That's going to affect our shear strain as we take a look at this over here like this here. This is our strain right there, our gamma right there for our shear strain. So as we continue on, we talk about torsion right there. Let's just discuss a little bit more in detail this shear strain, our gamma term right there. So now we can go back up here and we can see that this strain is going to be dependent upon this change in our angle, our CAB to CAD, where our CAB is in red up here, and initially this is at 90 degrees, and then it changed at 90 degrees, which is theta, and then this changes to this theta prime down here. So that's what we talk about right there. Our CAB initially at 90 degrees changes to a theta prime down here when we go now to CAD, and we follow that green line up to D right there. So this is going to relate back to our shear strain. So we can see that there is a relationship between our gamma, our shear strain, and our theta term as well right here. And it's based upon this relationship, this governing equation right here, that gamma is equal to pi over 2 minus that phi prime right there, which that phi prime right there is our new angle right there after deformation. We're going with CAD. So as we continue on with this here, I want to take a look at these two different triangles. We have two different triangles we're working with. We have this top triangle in red right here, which is our DAB triangle right there. So we start at DAB right there, and we see that this length in the side over here is our delta x term right there. And we also have this triangle in green right here, which is our D center B, where this is the center that we're talking about down right here. And we can see that this is going to be based upon our angle right here, our delta theta right there. So as we move forward with some other formulas right there, we might want to express these slightly differently. So we can use this delta x right here, the change in length right there, and this is going to be our dx in our expression right there, and our delta phi right here we can express as our d phi right there as we move forward with some of these relationships. So again, we pay attention to our delta phi right there is that change in the angle as we move right here across this from our undeformed plane to our deformed plane right there. There's that angle right there, which is our D center B, and our delta x is the side of this over here, and our triangle right here, our DAB. So as we move forward, we're going to start talking about some of these governing equations and formulas we're going to use. One thing right here is our arc length equations. This is something that's important. These aren't straight lines. These are curved lines. So therefore, we're going to be talking and using arc length within these right here. So within our arc length right here, what we have is our equation right here. So we can see down below, we have our BD is equal to our rho d phi equal to our gamma dx. So there's our d phi and our dx that relate back to what we just saw in our previous slide. So this is our BD, we can see drawn in red right there. So this arc length along right there here is equal to our rho, which is our length right here from our center point down here, this distance rho right here up to D right there, times that D phi right there, which we just talked about. This, our delta theta, is our D theta right there. Now this is also equal to our gamma term right here, or this gamma right there on this top triangle, DAB right there, times our delta x, which we then said is dx. So this is how we're going to get our arc length, is based upon those right there. Now from that, our question is, okay, well, how do we get our gamma, which is our shear strain? Well, we have our relationship for shear strain right here. We can rearrange these. We say that our shear strain is equal to our rho right here, radius of curvature, we just shown right on our graph there, or our diagram right there, times our d phi dx, our change in phi with respect to our x position right there. So then we can say, okay, well, d phi dx is a constant over the surface, and that phi is going to vary with our rho, and that's based upon this relationship that we see right here. Let's take a little bit closer look at our shear strain. Now what we can tell here is that our shear strain varies from 0 at the center of the cylinder to a max value, which is going to be our gamma max right there at the outer boundary at our radius C right there. So again, right at the center right there, it's 0 right at the center of our member right there, and then it's going to go out to a max value as we get out to our outer radius right there, C. And we've seen this over and over again before, but we're reiterating that, and that still applies right here for torsional deformation. We have our governing equation right here that our shear strain is equal to our rho times our d phi dx right there, where we have that change in that angle right there on the plane, and our change in our distance right there, and our x on the top triangle. So then we can rearrange that slightly, and we can say, well, what is our d phi dx? We can rearrange it and say d phi dx right there is equal to our gamma over rho. We can also rearrange that right there now and say, well, for our max right here, this is no longer gamma and rho, it's our gamma max, or our max shear strain right there, and our C is our outer radius, our total outer radius, so that R is equal to C when it's out that outer surface right there. Now we get this relationship shown here, the d phi dx is equal to our max shear strain right there divided by the outer radius, C at the boundary. So let's write down these equations again right here. Now we can see now, okay, for our gamma is equal to our rho d phi dx right there. What is our d phi? Well, there, if we look at a physical representation over here, take a slice of this right here on the hole right here. This is our center right down here. There's our outer radius C right there. There's our rho going up to the top of our element right there. So we can take a look at all that, and we can say, okay, there's our rho value right there that we're plugging in. There's our gamma that we're interested in right here. So we can see there's our gamma between these two angles right there. And then we have our gamma max up here at the outer surface. We have at the surface right here where this element is, if our element's down low, and our element right at the top surface as well. So there are two different elements that we're seeing here. I know it's a little bit tough to visualize in grayscale, but this is your element located at the outer surface. This is your element located at some distance right here, some radius rho right there. So you can see that's a gamma, and then this is our gamma max up top right there. So as we relate to our equations right here, our d phi dx right there is equal to this gamma over our rho right there. So there's this gamma right here. There's this rho right there. Whereas if we go to our max term right there, it's our d phi dx is equal to our gamma max over C, where there's our C when this is out right at the outer surface right there at C right there. And our gamma max is this right here as far as what we're looking at physically on this up at the top element at the outer surface. So we can rearrange that, and our relationship between our gamma and our gamma max right there is this is equal to, gamma is equal to rho over C times our gamma max right there. So as we continue on with our discussion of torsional formula right here, one thing that we want to take a look at is our relates as stress goes to strain right there. Now, in order to look at this right here, we can use Hooke's law, and this does apply where tau is equal to G times our gamma right there. Our shear stress is equal to our modular rigidity times our shear strain. But this is only for the case when the material is a linear elastic, homogeneous, and isotropic. So we need to make sure all three of those apply if we're going to utilize Hooke's law to go between stress and strain. So continuing on with that, the linear variation of the shear strain leads to the corresponding linear variation in shear stress. So we have this right here that our gamma is equal to our rho over C times our gamma max. And we can see there that tau is equal to, if we replace that for our shear stress rather than our shear strain, of our rho over C, where C again is that distance all the way out the outer surface, times our tau max there. Now this, the shear stress will be 0 at the center of the cylinder, and then at some maximum value when we get to that outer surface, tau max. We've seen that before there, so as we're looking at our circle right there, we can say, okay, we're all at the center right here, it's at 0, and as we get out here to our outer surface at C right there, that's where we're going to have our tau max. Now we can take a visual of that there a little better than my hand sketch right here. So what is our tau max? So we can see tau max is right here. So when we get out to that where our radius is equal to C right there on our rho, our radius of curvature axis right there, we go up and we can see that right here is our max right here on our tau axis over there. So we still have our shear stress is equal to rho over C. There's our rho over our value of C at the outside boundary right there times our tau max value there. So that's how we can relate our shear stress with our max shear stress right there. So within this here, we do want to make sure we pay attention to our right-hand rule right there, make sure we have our positive axis going out. And what we can do is we can sum up the shear stresses across all the possible elements. And that's something that's going to be important right there, as we want to consider this at all these different areas of interest right there. We sum them all up right there. This is going to be equal to the resultant of the internal torque, so T, at the section due to equilibrium right there. So we take a look and we can find our force dF for an element of an area with a face right here of our dA. So we can take a look over here and see there's our little element right there. There's our area right there, our dA on the face right there. Now we can use this relationship here that dF, that force dF is equal to our tau, our shear stress, times that area dA right there for that element right there. So dF causes a torque with the moment arm, the radial distance, rho, right there. So there's our radial distance, rho, right there. So that's our torque from that there. So now we can say that dt is equal to our rho df, which is then equal to, when we plug in a relationship for df up there, once we use that right there, this says that dt is equal to rho times our shear stress times dA. So the total torque that we're looking at here now, we can do that by doing an integral right here, summing all of those individual elements, right? So torque is equal to the integral of dt of all the individual torques right there. Well, torque we saw was our rho df, and we said that df was equal to tau dA. So now our total torque is equal to the integral over the area of our rho right there. There's that radius going out there, times our tau, our shear stress, times that the area of our differential element dA right there. So we can change that up a little bit here, and what we can say now is that our t is equal to the integral of a times rho times, now we can write this in right here for our tau dA right there. This is, we recall this information right there, that tau is equal to our rho over c times our tau max. So all we've done here is we replaced our shear stress right there with this relationship that we showed earlier right there, place that in there, and that's still with respect to dA right there. So torque is equal to the integral over area of rho times now this right here, rho over c tau max right there, dA. So we can do that there, pull out our constants. Well, our tau max over c right here is a constant. We can pull that out front of the integral right there. We say that our total torque is equal to integral over the area of our rho squared dA. So continuing on with our torsion formula here, we now want to solve for the maximum shear stress, our tau sub max right here. So this, we have a relationship we have here, our torque, our total torque is equal to, when we pulled out those constants from the integral right there, tau max over c, the integral of the area over of rho squared dA. What we saw here now is we can come up with this relationship here. How we can do that is we can go to equation 4.3 in our textbook, and we see that tau is equal to our Tc over J. Now, if tau is equal to Tc over J, we can rearrange this top formula right up here and solve this here for our J right there. So J would be equal to, if we do this right here, if we multiply the J over there, it's Tc over our tau max. So that's exactly what we have right there. So we have this now relationship here by plugging in equation 4.3 to that equation above, that J, our polar moment of inertia, is equal to our rho squared dA. How do we get from our max stress to torque right there? Well, we have our relationship right here where our tau max we just solved for from that relationship there that we saw in equation 4.3 in our textbook. And now we have a value here for our J right here for this particular case right here, where J is equal to pi over 2 times c to the fourth. So what we can do now is for our shear stress at any radial distance right there, we have the relationship here that tau is equal to our T times our rho over J. So that's at any radial distance rather than just at our outer surface right there. So the outer surface corresponds with the max. The rho is just for our normal shear stress. We have that relationship right there, where we could then plug in for our J values as well for this right here. So the assumption is for a circular shaft when we're using this relationship here, and a homogeneous isotropic material that's within its linear elasticity.